So he did the same thing that he did to be able to move imaginary or vectors that are on the imaginary or the complex plane to the real number plane or try to flip it. He did the same type of process when he was dealing with Quaternions. So he said, okay, so given a vector on the imaginary axis, what do we have to multiply? Ask the same question. What do we have to multiply that vector on the imaginary axis to get to the k-axis? This is just an example to get to the k-axis. It can be any axis because it's all relativistic. So what vector do we have to multiply? What number do we have to multiply a vector on the i-axis to get into the k-axis? Okay, that's what we're going to do right now. If we multiply it by I, that gives us I squared, which we know I squared is -1, which we know -1, which what would it do? Rotate it 180 degrees. Not going to work. Okay, if we multiply it by the k-axis, that would imply that I times k equals k, right? A vector on the i-axis times the k-axis would be on the k-axis again. That would imply that that would imply that the i-axis equals 1, which it does not. So these two ways are not going to work. But if we multiply a vector that's on the i-axis times the j-axis, well, that's going to give us the k-axis, and that works. That works just fine. And he ended up redoing that throughout all of it, or he ended up going through that multiple times, and he found, okay, what? I times j equals k, k times I equals j. And he goes around clockwise. But if we go counterclockwise, this is how he figured it out using this method. It's going to give us the same properties, except it's going to have a negative product. So j times I equals k, a negative k, k times j equals negative I, etc.